they become less and less accurate. Oftentimes, these meters are referred to as analog power meters. Some people believe that the analog power meter generates less magnetic interference than a modern electronic digital meter. However, the opposite is the case. Let's let Mr. Towns of Westinghouse explain the inner workings of an old-fashioned electromechanical meter. And later, I'll return in another segment and explain the inner workings of an electronic digital meter, and we'll make the comparison. There are two things to keep in mind about the old-fashioned meters. One, they are old, and they have many, many moving parts, which require adjustment to maintain accuracy, and they wear out over time. Secondly, in a single-phase residential meter, there are 3 magnetic coils, 2 current coils, and 1 voltage coil. These coils produce magnetic fields and consume valuable power. Let's listen to Mr. Towns. Part 1, Section A, is a simple but detailed explanation of the power meter for non-technical people. Part 1, Section B, is a much more mathematically based lesson on the actual scientific principles of how the magnetic power meter works. Utilities are now moving rapidly to replace these old-fashioned electromechanical meters as a priority set forth by the federal government. Our purpose in posting and discussing this information is to provide scientifically accurate and correct information to consumers concerning the differences of the old-fashioned electromechanical power meter and the modern 21st century meters.
Thermal. Okay. On this one over here, I go down, I go in the front and come out the bottom. So what have I done? I have effectively reversed one of those current coils, haven't I? I have reversed the way the current is going to shine it, so to speak. All right? Now, I can represent this thing vectorially. And this is a way of expressing something in relationship at a certain power factor. Let me go back to the 2-wire meter to show you an example of what I'm saying. I've got an E sub NA, which I apply to the voltage coil of that device. And what this is a way of representing that voltage at an instantaneous value of time. I am going to declare that the load which this meter is metering is a unity power factor load. That is, the voltage and the current are in phase. They're one on top of each other. There is no displacement between the voltage and the current. Therefore, when I draw a picture of the E sub NA and the IA, they appear to be together. Let me just show you something. A lot of people have different ways of looking at it. If I could just please believe me that this is an eye of somebody who's been up all night long. A red eye. And this thing is anchored solid in a 60 hertz system which we operate. This voltage, E sub NA, is going around this point here 60 times per second. Okay? What I'm going to do is I'm going to stand out here and look at this baby, and I'm going to watch it go around 60 times a second. And I'm going to bat my eyes and open up again. And I said, that's an instantaneous, which I looked at it. All right? I noticed that E sub NA is here, and I noticed that the current which is being drawn by that load is in phase with that voltage. It's instantaneous time. It looks like it is right there with it. Okay? Ah, yes. Now we go down here to Mr. 3-wire, and we go through the same gymnastics, so to speak. Here it is, the old eyeball over here, looking down at the point X, which happens to be right there. Okay? In this case, I have a voltage which goes from B to A. I'm going to call that E sub BA. I'm going to name it E sub BA. The currents that are in here are I sub NA and I sub B to N. I sub NA, which is this one right here, and I sub BN, this one right here, from here to here. If I put them in relationship to that voltage, I sub BA is right here, and I sub AB, which is down here, because they're the one and the same current. Now, because I have purposely reversed one of these coils, they now add together. And I can see that in a formula. The watts total is equal to E sub BA, that's that voltage right there, times I sub NA over 2. In other words, this is a half coil. That's the reason we got the 2 in there, or divided by 2, multiplied by the cosine of the angle between that voltage and current. If you'll get your backside of this paper on about page 29, you will see a trigonometric function table. And please believe me for the moment that that is a cosine of 0 degrees or 1.0, okay? In addition to that, I also have E sub BA reacting as I sub BN divided by 2 times the cosine. And those two quantities add up. I'll come out with 1/2 EI cosine theta plus 1/2 EI cosine theta, or the watts is equal to EI cosine theta. If it happens to be unity power factor, it's EI, voltage times current. Okay. Now that starts you out on the road to using vectors. From here on out, it becomes a little bit more difficult. I'll try to make it as slow as possible and try to finish up on time. But basically, this is a system wherein all loads can be represented by various mathematical dissertation. This is a very common polyphase type load. This happens to be a 3-phase, 3-wire delta. 3-phase, 3-wire delta, and it has 3 basic wires. Now you say, well, how in the world do you know where to put your arrows and your this and that and those on those things to make them come out properly? Well, I know that to meter this device from experience and other things, that I will have used a full current coil in this leg and a full current coil in this leg, as opposed to what we did a while ago with my single phase meter, where I used half turns, 2 wires for a single phase unit. These are going to be 2-wire type devices. Since it is a 3-wire device, it is, according to Blondel, a 2-stator meter requirement. 3 minus 1 is equal to 2 stators. 2 stators is all this meter has in it. Okay, I'm going to meter it A, B, C. I can take my eyeball and go out and do my thing, and I'll see that these voltages, E sub BA, E sub AC, and E sub CB, are 120 electrical degrees apart, and the way I know is I can plot them down here, and it looks somewhat like this. Okay? This is E sub CB. CB, you can just barely see it up here. CB is going across, and notice the relationship. Can I just pull that down a wee tad there so you can see all of them? Here is E sub CB. It's starting at a point here, and it's perfectly level going out to the right-hand side. Notice where I've got it plotted down here. Same way, same relationship. E sub BA, which is this voltage here, BA, A at the top up there. In fact, it's lettered for you. You'd see it very easily there. And finally, we got the other one with E sub AC. It ought to be heading that direction. Well, it happens to be E sub AC down here. Now, at this condition, unity power factor, that is no relationship between voltage and current in the load, but in the meter, it doesn't show up quite that way. As a matter of fact, if you'll follow along with me, we'll see what happens in this meter. I'm going to look at a point and find out what these currents are. One of the laws of the electrical business is that if you take currents about a point, that is a point like this, you can actually write a mathematical equation about those currents. Matter of fact, they happen to be that if you take IA and IEC and IBA and add them up, they got to be equal to 0, depending on which way the arrow is going in that particular relationship. If you look real close, you'll see why. IA is that particular current at the top moving out from that point, plus IEC. AC is that particular voltage current that you see over here, and minus IBA. IBA would be this one right here. Add those things up, be 0. Changing the sign to know IA is equal to IBA minus IAC. Just a manipulation of that particular unit. Knowing that, I can plot those things on this particular diagram, and I can write an equation for the total watts of that 3-phase, 3-wire delta meter. It comes out to be E sub CA, that's what's over here in this very top unit, times IA, which is that current. Let me get up here so I can see it. I'll sort of turn it down a little bit there. And, all right. It's this voltage right here, CA, IA times the cosine of 30 minus theta. You say, golly, where in the heck did that come from? Well, let's find these things first of all. Where is ECA? Well, it's minus ICA up there, so it's right here. And where is IA? Well, IA is right next door to it. Here they are, right here. What's the angle right in here? Well, if I took a protractor, I would soon find out in this 60-degree relationship and so on that there's 30 degrees in there. 30 degrees. So if I look down here, I say ECA times IA times the cosine of 30 degrees. Now, if I have my eye out here looking at this thing go around, A, B, C relationship, IA on a lagging condition, that is, if it was a load which was not unity power factor, was lagging, that is, it was like a glass of beer, had a lot of foam on it. You know, it's not quite 100%, a little less than 100%. Y'all laugh about that. Y'all had that example before, huh? I could have used a peanut blender, or I could have used the donkey, you know, chasing the carrot. But all those things which add up the power factor says if they are displaced, then they are going to give you a different relationship. As I can see this is going to happen right now, I have cosine of 30 minus theta. This is going to be moving in this direction as it lags. The poorer the power factor, the more IA is going to be in this relationship to CA. Okay? So I say it's IA minus that particular angle which it moves. Plus the fact I'm going to have E sub CB and IB working in there. E sub CB, where the heck is E sub CB? Oh, that's right here. And IB, that's elsewhere. They're also 30 degrees apart, aren't they? So I write the equation, E sub CB, IB, cosine 30, and as this current moves off, and all the currents are going to lag in a so-called clockwise direction. Then I sub B is going to move this direction, so that's going to be 30 plus theta. Now, back in high school, we had a formula that goes something like this. The cosine of two angles is a relationship which effectively boils down to cosine of one angle, cosine of the second angle, change the sign, and add sine of the angle and sine of the second angle. Let me put it up on the board so you know. If I have an angle cosine of this plus this in a relationship that I can do, it says cosine this, change the sign, sine that. There's what that baby equals to. You say, boy, that's a long ways around the thumb. It is a long ways around the thumb, but that's the way you have to add these things up. There's no other way you can do them. They come out just that way. Okay? And that's basically what I have done right down here. I have taken the first one and the second one. First one, second one. And I have put them down. EI, I'm assuming voltages and current are the same. And I mathematically expand that one into cosine 30, cosine 0, sine 30, sine 0, plus. The second one, of course, is a plus thing, so that one changes to a minus sign on the second relationship. I add these two devices together and I have EI times the square root of 3 over 2 plus EI plus the square root of 3 over 2, or EI square root of 3 cosine theta. And if you go to the good book and find out what the formula for the total watts in a three-phase, three-wire circuit, it'll say square root of 3 VI cosine theta. And that's what the meter measures for you that quickly. Okay? All right, now that's the first polyphase example. Let me ask if there's a question. Well, that particular one. Is there something in there that completely snows you that I should go back and do again, or I can help again? It's a mathematical way of expressing what a circuit is in relationship to that meter. It's going to meter that particular service. Now, this doesn't come easy. You're taking a 4-year engineering course in 5 minutes. But please believe me, if you'll take what you have here and a meterman's handbook and one of your buddies back there, you know, the guy who's supposed to be the engineer of the place or somebody who has some electrical knowledge, you know, sit down and you become familiar with these things, and boy, this is a real valuable tool to have in your toolbox. No question about it. Does a beautiful job. But it's not all this difficult. There are a number of things that can happen to us. Let's just go ahead and go to the next one and see what it looks like in relationship to what we just did. Here is that question that I said I was going to promise you. The boss says, hey, what % registration is going to happen out here at XYZ crossing when they found out that the wire was broken down here at C? What do you think the meter is going to register if that happens to you? Well, what you do, since you know that the load is a 240 volt load, 30 power factor, 100%, therefore we know if the thing was operating properly, we'd have a square root of 3 VI cosine theta. That's exactly the formula we just got through going through, right? And if this thing was operating properly, 240 volts and 30 amperes on it, we'd have 12,470 watt load. That's what we'd have on there. That figures out to be, you know, kWh, 12.47 kW, which is a nice load. I mean, it'll sit there and grind in a few dollars per day and help pay our salary and so forth. But only if it's doing what it's supposed to do. Here is a case in point where they found out that somebody is, you know, didn't tighten the screw down just right, or something happened. You know, it could be a rat gnawed it in two and committed suicide and all that. It could be a dozen things. But it just didn't come loose accidentally, so to speak, but some way. And when it did, here's what happened. Notice that you get a connection right here, goes through this volt coil, down through this wire, and it comes down here where it normally, uh-oh, that's open. And it comes down here and it goes backwards through that volt coil or wire, and finally ends up right there. So actually these two coils, the volt coils of the meter, are now in series. One of them is backwards and both of them are hooked across AB. That's exactly what happens. Believe that? Meantime, back at the ranch, the load of 30 amperes is still flowing through this current coil, or 30 amperes are flowing through that current coil. This is the load out here, which we know is 12.47 kW load. How can we tell how much we lost? Or maybe we were fortunate, maybe we gained. Well, you'd be lucky if it gains. Very seldom they ever gain. I'll show you in a few minutes about how it gains. But let's see what this one does if this happens to us. You've got to sit down some way to visualize what happens to you. In this case, we know that the voltage applied in this case is E sub BA, to those coils, one in series with the other one of them backwards, such that we see E sub BA over 2 in one direction, E sub AB over 2 in the second direction. And since these are delta devices setting 120 degrees apart, I sub A and I sub B is in there at their proper relationship. If I write the formulas for this, I will see that what this device is going to do is have a voltage applied to it and a current applied to it, which is normal, but you're going to have a 30 plus theta on one side and a 30 minus theta on the other. And if I grind in the values and work them out, both situations are going to give me a square root of 3 over 2 times 240 times 30